All right, good morning. We'll get started. I know Professor Eager is still talking about a lot of economics associated with selecting materials. I think we can all agree that we're not going to build roads out of aluminum castings or anything like it. We're really going to go with the, whatever works and is least expensive. If you remember, this is our 5th lecture in terms of materials processing. We started with solidification, and I did bring that part, and I'm bringing it again because we're doing another part of it today. We're doing a heat treatment on this. So we talked about solidification, then I talked a lot about deformation processing, how from the cast structure where you have all the dendrites, you go on and you want to refine the microstructure. So you break it down, the grains, they become strained, and then they recrystallize. You're at high temperature, so you get the composition to become more homogeneous between the very center and the surface. Last time, we specifically talked about rolling, and I mentioned that, it's a relatively high temperature process. The steel, for example, if we're dealing with steel, is red. If we're talking about aluminum, it could be much colder temperature, of course. But with steel, a lot of times you don't need to heat the steel as you go. There's enough deformation generated during the rolling process to keep the steel hot and red. We went through a lot of different processes quickly. We didn't really spend. There's a full 12-hour module on forming on the website that you can, if that's something you want to do for your online module, you're more than welcome to. It's very useful if you want to be involved with selecting processes for forming materials. Stretch forming is an example I gave with all the aircraft fuselage. We didn't talk too much about the bending operation. I said it's used a lot, and you shear the material. Deep drawing is what you do for the aluminum cans or the propane canister I brought last time. Extrusion is used a lot with aluminum. Wire drawing speaks for itself. Forging, we talked about forging, that you can have multiple axes and make very complex parts. A lot of times you do it progressively. And if you remember where we left off last week together, I was starting to talk about steel and the quenching process. So I was saying you heat up the steel, it becomes a single phase, and that's called the austenite. And we can put that some in writing because I remember there were quite a few questions after the class. And I know most of you are probably still scared of the phase diagram. The good news is we're going to go through some more details of that today, and it's going to be a simpler phase diagram. So we have the austenite, and it's stable at relatively high temperature. If you remember the diagram, it's around 750 to 850 centigrade. So that's red steel. So what happens is, first of all, you quench. That's, brings on a lot of potential distortion. There's a lot going on during the quenching process. Because you will have a phase transformation. That austenite that you have at high temperature is just not wanting to stay at ambient temperature unless you've put on a lot of alloying element. If we start talking about alloy steel or stainless steel, there are stainless steel that are austenite at ambient temperature. and they used for low temperature application because the austenite, if you remember, is, well, I don't know that I even said that, but it's the face-centered cubic. It's this structure that has more ductility intrinsically. So it's essentially the same structure as aluminum and copper at high temperature. And what happens during the quenching process, the austenite wants to go to the equilibrium if it's carbon steel. And that means one or two things. It could go to the equilibrium. The equilibrium is, for low carbon steel, is almost pure iron. So these are the white grains. And cementite, which is essentially a combination of, well, this phase here is the eutectoid or the eutectic. So it's a two-phase region. It contains cementite, and it also has the almost pure iron phase. So it's a multiple process taking place. The first thing that happens on low carbon steel is you form those. And these are, again, almost pure, almost no carbon in them. It's pushing the carbon a little bit towards the eutectoid, and then all at once you separate the carbon. The carbon goes to the black here, and then you get another white. That's very typical of structural steel. The steel that we use for car body panels, the beams, a lot of construction material. Everything that's going to be welded typically has this type of structure. If we're talking about a higher strength steel, you go through that quenching process. So here I was talking about cooling quickly, like the image shows. If you go very quickly in your cooling, you quench in water, for example, you form that martensite, and that's the tetragonal face. So if you think of something very cubic that has all these symmetry, and then all of a sudden one side becomes longer, the reason it becomes longer, there's a little piece of carbon that comes in there, and then all of a sudden you lose a lot of symmetry, you lose a lot of slip planes, and that is the martensite. So and I'm mentioning it just because Professor Eager talks a lot about steel, and I want you to start thinking about it. And we're going to cover that more tomorrow with respect to the process with steel. If you remember, one thing I said is we don't use it this way. It's too brittle. And we go through some processes after that, and that is called tempering. It's kind of, you remove some temper into the steel. You're not creating a temper. It becomes nicer and more happy. So that really was what I wanted to get at. It's one of the first real, hardening processes that was used, this quench. It's used to make tool steels. It's used to make high-strength steel. I believe in the first class I showed you some of the frame design for ATVs, snowmobiles, any kind of high-strength steel there went through this whole process. So it was hot roll form in tubes, quench, and tempered, because you want a combination of strength and ductility. There's a cost associated with it, and one of the main implications when you have a material like this, if you're going to go and weld it, if you're going back through solidification and very rapid cooling, so you're going to be closer to that quench situation, and it's going to be very brittle. So there are a lot of limitations in terms of using high-strength steel, not just because of their cost, but because of limitations for welding, for joining. If it wasn't for having to do post-weld heat treatment, we would be probably using more of this type of steel for construction, because you can minimize the weight, you can just increase your allowable stress. But a lot of structures are welded, and therefore we don't go that route. All right, so heat treatment. Most of the times there's going to be a phase transformation. Sometimes it's just a little piece of the structure that is changing. And that's what we're going to talk about today for aluminum. It's called dispersion strengthening. And I'll give you some examples. I got this casting here again. So I think it's important. You guys are smart. I want you to think about exactly how it comes about. The phase transformation, this is a much simpler phase diagram. So you can do nickel and copper. It's not one of the mostly used alloy, but it's another way to exemplify what happens when you have a change in microstructure. So we go to the liquid first. That's the high temperature. And we have an alloy that has 35% nickel in copper. When we reach that point B, we start to solidify. What's at equilibrium here? Between these two lines, it's a two-phase region. It's very, very different. So on a phase diagram like this, that's exactly how it works. You work for one phase, two phase, one phase. There's always a change. When you have that interface, it means something is happening. So in that two-phase region, at a certain temperature, the only equilibrium state, for example, at the temperature at the point C, is to have a liquid with this composition, so to have less nickel, and then you have this solid with higher nickel content. How the material knows that? The solid is always going to have a preference. It's always going to have a certain ratio that it's more comfortable. It's a lower energy state. The liquid, on the other hand, also has a dynamic, but it's a very different dynamic. Things are not organized. So as you go from point B to point D, you see your microstructure keeps changing. At the beginning, you have just a little bit. Then you keep having a little bit more of that phase, and you keep having a little more. Now, this schematic is if you have diffusion. So what that means is I started here to solidify these little particles. I had 43% nickel in them, and I was going slow enough that that nickel was able to diffuse out of the solid back into the liquid, so at the end everything is at 35%. In practice, it doesn't happen. It almost never happens. But the phase diagram, if you follow it, if you go very slowly, that's what will happen. So you end up with just one phase at that lower temperature. If you go more quickly, we can already envision a little bit like what I've shown with the steel, that you start forming that one phase, the composition, the liquid changes, and then you're going to have another phase or another concentration when that liquid solidifies, because it's not going back to exchange. So the diffusion in the solid is really, and there's a whole book about these phase transformation that I like very much. It's not very complicated, actually. It's got some illustration, and it goes from the very beginning to more complicated. The diffusion in the solid is very rare, except when we're going through that deformation processing that we've talked about. So let's take another example where we don't have the diffusion now. And essentially the same diagram. So we're still going to solidify, but it's going to take much more time because our concentration in the liquid keeps going down. We're using the nickel at the very beginning here, and we keep it. We still have the center here at 46%. We still have it at 46%. We still have it. And then at this lower temperature here, close to 1200, we still have a liquid. And it's really what happens with all the cast iron and all the steels. If you're going, at reasonable pace, you're going to have all that change and segregation. You're going to have a different composition in the different, where you're nucleated, you're going to have that high temperature equilibrium condition, and then at lower temperature, you're left with the extra alloying element that, couldn't fit in, or the system didn't want in the solid to begin with. Yes?
What's the change in conditions between this and the previous one?
Just the cooling rate. So over here, you're going very, very, very slowly, okay, and the diffusion is taking place. And we become completely solid. What temperature? So say around 1220. And over here, we still have our schematics here at 1175 or so. We still have a liquid, because we still have that, well, it's the last bit of it. This doesn't go to 0, so if I take it to 0, I could have 10, 0, yeah, right here. I'm going to have a liquid potentially all the way to 1100 in this, for this particular situation where we're cooling really fast. So it's something you need to keep in mind when we're going to be talking about aluminum alloy. The other thing that happens, I already given a clue with aluminum, we're not going to be looking at the whole microstructure changing from that FCC phase to the martensite, the tetragonal phase. So we're looking at little particles that are going to start in the bulk of the aluminum, and they're going to have a very different composition. What happens is you're going to need a critical size to form these particles, and all these concepts of interface stability really comes into play. If you're going to have a liquid and a solid, this actually comes very handy in welding. If you try to weld, like you just go to a shop, you try to weld, and your bead of steel is just really on top of what you're trying to weld to, your base material. What it means is you're not creating enough fusion, you're not creating enough equilibrium with your base material. If you have equilibrium here, you tend to reduce that angle, so the liquid is going to wet very nicely with the solid if it's hot. If it's really cold, then this particle is going to shrink here and come back, and it's going to be more of a half circle. So high interfacial energy will give you something that's closer to this, and low interfacial energy, say you heat your substrate a lot, is going to be closer to this. It's going to spread. The extreme case is a solder. The solder just penetrates into a joint because it decreases the interface energy. The reason why it matters is we've discussed for solidification, you're always going to have this critical volume that you need to make the phase transformation. We were essentially dealing with a liquid, and I was saying, well, if I want a little piece of solid, yes?
So why does the wetting angle change so much with temperature? Is that because the surface energy or the surface tension is changing?
Surface tension is reducing, yeah, when the solid temperature is going up. So say this is the liquid, and what I'm changing really is the temperature of the substrate. In welding, you can have the situation where it's actually coming back on itself. So and it's the extreme scenario. So you get the bead that is a little bit like this, and that almost guarantee you that you didn't have enough temperature to fuse the base material here. That's how we use it in practice. The nucleation stuff is slightly different because essentially you have two conditions. You're going to try to grow from something existing in your microstructure, and you're going to have that critical size. So here it's shown as a grain boundary. You start from a grain boundary, and you try to grow this new structure. And you're only going to grow it if you can assemble, say, 1 million atoms together and organize it. So it takes time, and it takes diffusion, because you start with the composition being the same, and then all of a sudden, say you want 20% more of the nickel, if we go back to our example. So you need that 20% all of a sudden be there just through thermal activation. So nickel is going on in the microstructure. Things keep moving, moving, moving. At one point in time, you happen to have all that material in one spot, and it will grow instead of disappearing back. So it's really this, think of it as having noise in a system, and instead of losing the noise, when it's stable, it will grow on you. Now, let's try to apply that to aluminum alloys. It's used, except if you're going to have use aluminum as a conductor. If you use aluminum as a conductor, a lot of times you want almost pure aluminum just for electrical conductivity. If you have other applications that are more for mechanical strength, you want to have alloying element in your aluminum. It's really easy and cheap to increase the strength, and not so much the ductility. It's some of the ductility. It depends on the alloy, but you really increase the yield strength by adding a little bit of alloying element. And so we're talking about only 4% or so. So it's not something, even if you have 4% copper in aluminum, you're not really changing your benefit of reduced weight. It still, performs much better than steel on a strength per weight basis. Let's clean this up. So that's what we're going to study more specifically. Copper. And we're in the range of 3 to 5 weight percent. You can use a lot of other things. You can use magnesium is used a lot. You can use some manganese, but the manganese does a very slightly different behavior. You can add zinc. Copper is typical of the 2000 series, so one of the very common aluminum grade for aerospace applications is Aluminum Association 2024 T6, and we're going to discuss this. That refers to the treatment. So this is just really just an example for you. But and then you have other series of aluminum that will have different properties. So that's what we're going to focus on. Essentially, the concept of adding a little bit of copper and creating little precipitates that will be dispersed and increase your strength as much as a factor of 3. So let's go through that. The phase diagram. Aluminum here for our purposes, copper the other side. What we are interested in is this region where we have one phase, a little bit like we had the austenite. So here we have aluminum that's willing to take on a certain amount of copper. Up to about 4 or 5% is the actual phase diagram. Let's not worry about all these transformations. We're just dealing with the first one there. This is more of a essentially forming cast iron or forming the martensite. So we're only dealing with A right now. Precipitation strengthening, it's essentially the alloy at high temperature. When you cool it off, it's rejecting. It's saying, I don't want this copper anymore because it's heavier, and I want to separate it from my structure. So the phase diagram tells me if I'm going on this case here with 3%, then I'm going to end up with almost pure aluminum and then almost pure copper. I want two phases. Now, Do I get those two phases? Depends on how fast you are cooling. So when we do this, if you cool very slowly, you can have these big pieces in the microstructure. So you can have a relatively large grain of copper that's going to start forming and grow into the aluminum. That doesn't give us much good, and I'll explain a little bit. So if I have a microstructure that have aluminum and 3% copper, so if I made something, if I'm just looking under the microscope, that has a lot of grains, and I have a very hard one, and it's surrounded by a bunch of soft one. This is a little bit like a piece of wood in the river, a floating log. It's not going to change much of anything in the flow or anything that's going on. It's just going to be carried with everything else. So we really want to avoid any situation of having a big particle that's harder in a large volume of softer material. And that's where the word dispersion come in. We're going to really put this material very, very closely spaced. And in the practice of things for aluminum, the only way we do that is we quench it and then we heat it back up. So the quenching is called quenching as well, but it's very different than the steel, because when you quench, all you do is you freeze that structure that was the high temperature structure. There's no really other phase, there's no martensite forming, so you have one phase that just has extra copper in the microstructure. So we're avoiding, this is the one thing we really just don't want to have. So what we're doing, I quench it, and then I look at it under the microscope, there's nothing. I mean, you have grain boundaries, but everything is of the same composition. You haven't changed the strength. It's fairly low strength. So what happens then, you essentially have one phase that's super saturated with that copper, and when you heat it back up, it's called aging. So we go through quenching, and then we do the aging. And that's pretty, you could probably age it in your toaster oven at home in terms of the temperature range you're looking at. It's not high temperature. Some aluminum alloys, when I'm mentioning about the 2024, will age some even at ambient temperature. So you quench them and you let them sit there, and you'll start forming these little particles. So what these little particles do, I think you're starting to get the idea, is they get into the microstructure inside the grains. So I have one grain here, and I have multiple, many little precipitates. And these are the ones that are going to give you strength. Yes?
What happens if you have both that are completely melted, and I guess they're mixed together, and then you quenched it, just froze it immediately? So like spinning it on a copper disk or something.
You have the copper where?
No,
I'm missing.
So you're basically saying that if you freeze it, while
Yep.
you have small precipitates inside, that it's just going to keep that shape and structure.
You don't have the precipitate yet, because they wouldn't form that way. If you're at high temperature, you have so much diffusion that if you have one little particle that starts forming, it's going to grow on you. And therefore, we can't just do it by cooling. That's why we quench. And when we heat back up, the condition we have is there's a big driving force. There's a lot of reduction in energy to be gained by combining everything. At the same time, it's a lot harder to get all the atoms to be at the same point at the same time. We don't have as much noise. So when the noise takes place, oh, I'm forming one. But it doesn't really grow very quickly, and that's why you get many. So any process that happens on a very high driving force, that's what we're trying to do. We're increasing the driving force, and we're reducing the growth rate. So it nucleates quickly, it takes time to grow, you get many. It's pretty much the bottom line. If you were closer to the equilibrium temperature, the driving force to form them is very small, so the first, when they form, they're gonna have to be really big, and they're going to continue to grow very quickly because of the diffusion. It's a good question. Thank you. Yes?
If you're aging at room temperature, how do you make it stop, like for these aerospace alloys? How do you make them stop burning?
Very good question. A lot of times you will wait. It's not going to be very long that you're going to use all your copper. And we'll get to, and then what happens is if you stay, you get these very small particles. If you stay, they're going to start combining. And now all of a sudden, you have bigger and bigger. And it's a big sequence. I think it's we're pretty much there. Yeah, let's talk about that. This is the different phases that you're forming. Over here, it's a TM image, so it's showing particles that are of the order of 100 nanometers here, these little circles. These are the ones that forms if you age at very low temperature. And this is a part that's a little less intuitive, but I think you can still see it. We're still talking about noise here. So if I have, say I'm putting just 1,000 here of little solid particle into the microscope, there will be one point in time where they'll move. There's nothing to say that that solid particle, if it's very small like this at the, it's, you know, it's very, we're talking about transmission electron microscope. This is 100,000 magnification, and there'll be a point in time where I have two particles close together and they combine. So I'm reducing the number of them and I'm increasing their size. But it's very early on that you use all your copper for that transformation, and then it's just a matter of how it's distributed in terms of size. The bigger the size, the less you're going to have of them. And they identify them at the very beginning. At this size, the precipitates can be disc. They have very different shapes because they conform with the crystal. They are still part of the crystal. They're not a separate phase. So we call these coherent precipitates. And then as you grow in size, there'll be a point where you know, just the structure is going to have its own density and size, and it will start forming an interface to the equivalent of a grain boundary after a while. What we try to do, if you remember all my discussion on dislocations, you try to have them in the crystal, because in the crystal is where all these dislocations are going, and that's what we're trying to slow down if we're going to increase strain. So it seems like a lot of work, but the reality is for aluminum, we're only talking about heating it up, quenching it sometime in oil, it's enough. Nothing happens, and then you age it at low temperature to develop that strain. It's really worthwhile. And the reason why it works is you prevent the microstructure to follow the phase diagram. You refuse to have all these big phases. And then after a while, you go heat it up and get the exact size of precipitates you want. So there's a relationship between the temperature you're going to go at, the time you should wait to get your strain. And this is for different alloys. So we have different concentration of copper from 1%. So if that's your budget, you only want to pay for 1% copper, you're not getting a whole lot. But by the time you're reaching in the middle range here, 2.5%, 3% is where you start increasing your hardness. So that's the scale of hardness, how the hardness is changing over time. And that's more or less this factor of 2 or 3, depending on the alloy. It goes through a peak, and I think now you have all the background to understand it. So you're going from, at the beginning here, you still have some strain because the copper is in the crystal. and it's a very different density, it's going to slow down the dislocation. So that's called solid solution strengthening. But what really we're looking at with the aluminum alloys is we're looking for these particles to become a different, the alloying to become a different phase, and that's really where the strength increase goes up here. And later down, when you reach a certain size, and these are the third generation, second or third generation, they are semi-coherent. So they will stretch the lattice in one direction sometimes and not in the other. And that's the size that happens to slow down the dislocations the most. I have seen that firsthand, but let's go back to, I know there's something I was missing. Okay. Nucleation and growth. What's interesting here is we're looking at what happens depending on at which temperature you're going to be at in terms of nucleating grains. They're showing for two composition. We can just look at one of these curves. If we're close to the equilibrium, so for condition 1, we have to go down in temperature up until, much further. So 1/3 down, right over here, is where it doesn't work. We start seeing some nucleation. So it's exactly what I was saying, where if you don't have enough departure from equilibrium to account for all the surface creation, you need such a big piece that it's not gonna nucleate. Then eventually you'll reach a condition that where you have both. You essentially need both. If nothing was ever going to move, and you always have a driving force, you always need a critical size, it's never going to happen by itself. So you need that fluctuation to take place, and you need a driving force. And there's a recipe, there's a combination in between where your nucleation rate is the highest. That's really what we do in aging. So you take it all the way down. When you're all the way down, you don't really have much nucleation taking place. And then you decide at which temperature you take it back up in the process. It's not typically a problem with aluminum to cool the whole section, because aluminum has a lot of thermal conductivity. So when you cool it, it will cool through the thickness. But all these processes with heat treatment, when we're going to talk about steel, are a little bit more of a trouble, where you don't really get the same cooling rate on the center than on the surface. And therefore, you're getting these different kinetics in the two regions. It's harder to get the center of a piece hard, because it's harder to go through all that sequence of processes. Yes?
Sort of going back to this precipitation argument.
Yep.
What's sort of like the difference in driving force for like homogeneous versus heterogeneous nucleation, like at the grain boundaries? How do you control? I feel like what's preventing the precipitates from nucleating and growing from the grain boundaries?
Okay. Yes. So it's a very good question. If you're at high temperature, you almost need to be at a grain boundary to start. To minimize that critical size. It's essentially, it ends up being, like I've shown on this sketch, and you start from a triple grain boundary. So you already have 3 interfaces to begin with, and you're just sort of eliminating one.
part of the aging process takes place at a low enough temperature, and the driving force just allows for homogeneous.
So if I have these 3 grain, I'm just trying to be in the middle here with my new structure. So I've eliminated practically some interfaces here. If you go slow, that's what's going to happen. So you have grains of copper. The idea is, like you said, you go fast enough that it will still happen, but it will grow slowly, and you'll have all of those in the grains themselves forming at the same time. And what becomes important is what is in the grain for strengthening. So that's why there is no real way to avoid having the quenching process. You're not going to get there, which is probably what you were thinking. It's a lot of different things. You know, I've been dealing with this for a while now, so trying to. So reduce interfaces here. You'll have it. You know, if I'm going through the quenching process and I heat it back up, if I go to the TEM, yeah, there's going to be one lucky guy right there. But we don't care, because overall what we're looking at is to have them inside the grains here. And I don't even think there's much segregation in the grain boundaries. Yes?
What's to prevent the existing precipitates from just accumulating more atoms and then actually just growing larger and larger rather than a pattern of tiny precipitates?
It will happen. You can't use aluminum on the aircraft anywhere near the engine. Sometimes you have to worry even about de-icing system, like when they come and there's ice on the aircraft, because if you heat it back up, then you gradually go and things will coalesce into a bigger and bigger grains up to the point where it doesn't provide any strength, and it's very harmful sometimes in terms of corrosion resistance and other things when you have 2 phases. Yes?
Even on aircraft grade aluminum, like 775, how hot do you have to get it for it to start noticing that?
Oh, now you're testing me. The 70-75 can take a little bit more, but you know, I think when you go above boiling, typically with aluminum, you really start wondering, you know, if you're going to lose significant strength. If it's the skin, sometimes it's okay, you know, but if it's the primary structure, it's a problem. And I've actually worked on a project where, because of the de-icing system, the engineers decided to switch from aluminum to titanium for the rib structure, for kind of the truss that are inside the wings. And that came at a very high cost. It's one of those things, they were late in the development stage when they did the detail analysis. And then they wanted to switch. At the beginning, they were machining all that titanium out of plates, so they wanted to do castings, and that's really what I was working on. So it's a lot cheaper if you can cast it, but there was issues with all the quality control and inspection, additional inspection you need to do if you're going to use a casted component for a main structure. But the idea with the aluminum is sometimes you can afford a little bit of that lost in strength. You know, we talk about a change, but it's a limitation. You can have you know, even in brakes, you can have some aluminum alloys. You know, they're going to be designed a certain way for wear resistance, but a lot of it you can lose when you heat it up. Most of it. All right. So I wanted to exemplify this situation with what you do on that curve here. It's nice to have a lot of decision power. So if you look at this, Like, okay, what do I want to do? Do I want to go right in the middle? I get the maximum hardness. Do I want to be slightly below? Do I want to be slightly above? And the answer is it depends on exactly what you're trying to do with the aluminum. If you're looking for the best ductility you can think of, lots of times you're going to try to be at the peak or sometime a little bit before the peak. And what happens there is we know we have the smaller particles. So they're going to interact with the dislocation in a different way. They actually create more hardening. More particles, more hardening. Think of it that way. When you're a little bit past the peak, the advantage there is typically just pitting corrosion of aluminum in chloride environment. If you have your precipitates that are bigger and a little bit more separated, the energy of the grain is slightly lower, and you're just improving your pitting resistance. So it's just a question of, you know, exactly how you want to optimize it. Now, one thing I did for my thesis, I took an aluminum alloy and I studied for the same hardness what happened before and after. And the way I did it is this process here of deforming. It's the scratch experiment. I think I mentioned it a little bit at the beginning of the class. I'm having a startup on this right now. So what you do is instead of indenting and doing a hardness test with the material, you move the tip, or in this case, you move the material, and it's plowing. So it's forming a lot of strain. If I'm looking at this scale here, where you see red, you're at 400% strain in the material because you have the friction and you're plowing it. So it's about 5 times more strain that you get through a hardness test. So it shows a lot about how the material will harden. When the material hardens, what happens is it doesn't want to form that ridge. You see the ridge on the side, it doesn't form it as high. And this is the experiment. I did this in the nanomechanical lab on the Infinite Corridor. If you're underaged, which is before the peak in hardness here, this is the aging time. So before you go through the peak, at this temperature, at this condition as received, you see you get much less material on each side of the scratch than for the same material, exactly the same hardness, but past the peak. So in this case, we have bigger precipitate. So it's a way to show you how important strain hardening can be for, you know, in terms of wear resistance, for example. If you really want something that's wear resistant, you're looking at bearings. We use a lot of precipitation, hardening, stainless steel for bearings. And without going through all the details, it's the same thing. You start forming very, very little particle in the matrix of stainless steel, the same way that we discussed today for the aluminum. Yes?
How does the slope of that age sample curve diminish with time?
We're talking from here to here, or I'm missing something?
Yeah, why is the slope negative? I thought the whole point was that as the longer you age, the harder
Yeah.
you get.
So what happens is this comes already with some temper. It started as a T3, so we don't see as much the beginning. I got 2 points here, but you know it should show more of the increase here and then the decrease. If it came straight off the quench, it'd be different, but it's exactly that 2024 type material that actually ages at ambient temperature. All right, guys, thank you very much. And if you have any questions, you can come see me.